In this lecture, I would like to show you the idea of hydraulic head in Francis turbine. The hydraulic head is a value that measures the amount of mechanical energy available in water in a river, stream, or even lake. The hydraulic head is equivalent to the water level in a static water body. In its simplest form, hydraulic head is a measurement of the head of a static water column above an arbitrary point, usually expressed in meters. The higher the water level or hydraulic head, the more energy that the water at a specific location has. So the very simple one is the hydraulic head here is actually containing the same meaning with the manometric head. But the idea of manometric means they are showing about the height that the water can go. So that's why we call it as a manometric or manometer. But for the hydraulic head here, it is referred to the how many energy that contain in that water supply. So means the potential energy inside that water. So it will refers to the water level at the top here to the level to the center point of the turbine. So this is the basic idea of hydraulic head. The higher the water means the higher the potential energy means that it could give high velocity at the inlet here. So mean high velocity means it could rotate the blade here very high, means it could rotate the generator very high, so it could give more electricity. Okay, so this is the idea of hydraulic head. So and then the effective head. So there are a variety of losses known as head loss. These head losses occur as a result of friction in pipe. When head losses are counted for, the actual amount of energy that can be harnessed is reduced. This reduced value for hydraulic head with the losses accounted for is known as the effective head. So the effective head is actually the real energy amount inside that water at the inlet of the turbine here. So this is the inlet of the turbine. So means that at this point, maybe you have 100 of energy. You have 100 of energy. However, when the water flow inside this pipe and so on, there is a lot of losses. Maybe at the starting point of the turbine here, okay, the energy inside the water is become 80 only. So means that the 20% is lost along the way here. Now the energy, 80 energy here is actually the effective energy. Okay, so that's why we call the effective head. So means that the effective head is the energy head at the inlet of the turbine. That is the simple definition of effective head. And then we go for the power input. Okay, so normally what happened outside here is actually not counted, not so important. The important one is what happened at the beginning of the turbine, because this is the main important point to rotate a turbine. So we will have the power input, and the power input can be calculated as this one. So the common equation for power is rho GQH, and then we need to use the H effective, mean the energy head at the inlet of this turbine. Okay, we are using the head here to calculate the power input, because this is actually the power input that start to give to the blade. So however, if there are no losses along this path, okay, you may take H effective equivalent to H hydraulic. Then we have hydraulic efficiency. Because we have power, so means that we could calculate the power in and the power out. So when we could calculate the ratio of power in and power out, means we could calculate the efficiency. So because this efficiency actually only reflected what happened inside the turbine here, so we call this efficiency is hydraulic efficiency, because this efficiency only telling us about the input idea of this one, okay, the input energy here, and also the output energy at this level. So this is just the energy changes across the runner. So only that 2 points. Okay, for hydraulic efficiency, so the basic equation is power out divided by power in. So if you see this device, the power out here is actually the Euler head. So means you need to calculate what happened after it's traveled through the blade. So it is the Euler head. So you will use the power out as the Euler head here as the power out, and then you will use the inlet head, which is the first energy that hit the blade, as rho GQH effective. So and then you could simplify the equation like this. So if you see this equation, you will find that this equation actually reverse with the equation of manometric efficiency. In manometric efficiency, you will have GHM over U2 V2 minus U1 V1. But for hydraulic efficiency, the equation is quite similar, but it's changed. The sequence is quite uh, reverse. So you will have U1 V1 minus U2 V2 over GH effective. So and then we have mechanical efficiency. So again, the mechanical efficiency means we need to know what is the efficiency of the mechanical part that attached to the turbine. Okay, maybe if you have very old mechanical part here, so there is a lot of resistance, a lot of wear and tear, so means that it cannot rotate very well, so mean you need more energy to overcome the friction. So the basic idea is still the same, the power out divided by the power in. Okay, however, you need to understand where is the power in and where is the power out. So in this situation, you will find that the power, the energy from the turbine is at point number 3. And then it will go through the mechanical part here. Okay. Okay. And then you will have another type of energy, which is electricity. So mean according to this diagram, you will find that this is the inlet. So means now the power in here is rho GQ HE. And then the power out here means the power that can be supplied to the national grid. So this is the final product of your electricity dam. So means this is the power output. So the power output here, okay, normally in our syllabus, it will be given as straightforward in the question. So again, in this situation, please make sure that you understand which one is output, which one is input. Because Euler head alone is cannot be determined as input or output. It's depend on the situation. It's depend on the definition. What kind of parameter that you want to calculate. And the last one is the overall efficiency. So overall efficiency, as you know, it is actually the idea from here. So, and then until it can be transferred to the national grid line. So here, as the power input, so the calculation for power input is rho GQH effective. So, and then the power out here is the amount of energy that can be produced and put into the national grid line.